Let's see the steps for constructing root locus. The first step involved is location of poles and zeros. From the given open loop transfer function, we have to find out the open loop poles and zeros. Then you have to place them in the S-plane. S-plane is nothing but, it consists of real axis, x-axis, positive real axis and negative real axis. And this y-axis is the j omega axis. This is imaginary axis. Positive imaginary and negative imaginary. So this is nothing but the S-plane. Now poles are denoted by cross and zeros are denoted by dot. So let's take this example. If the given open loop transfer function g of s is equal to k into s plus 1 by s plus 2 into s plus 3. So in this equation, if you find the roots of numerator, those are nothing but the zeros. If you find the roots of denominator, those are nothing but the poles. So numerator we have s plus 1. So equate it to 0. S plus 1 is equal to 0. Then from this s is equal to minus 1. This is 0. We have 1 0, that is minus 1. Next, equate this denominator to 0. S plus 2 is equal to 0. Then s is equal to minus 2. So pole number 1 is minus 2. Next, s plus 3. Equate it to 0. Then s is equal to minus 3. So pole number 2 is minus 3. We have 1 0 and 2 poles in the given transfer function. Now denote these poles and zeros in the S-plane. So what is the first pole? We have minus 2. So first mark this 0, minus 1, minus 2 and this is minus 3. So at minus 1 we have a 0. So 0 will be indicated as dot. So indicate like this. Next, poles minus 2, minus 3. These two are the poles. So poles will be indicated with cross at minus 2 and at minus 3. So this is the denotion of poles and zeros. So first step, we have to locate the poles and zeros in the S-plane. From the given transfer function, find out the open loop poles and zeros by finding the roots of numerator polynomial and denominator polynomial. Numerator roots gives you zeros and denominator roots gives you poles. Coming to the next step, and so let's see, before coming to the second step, the number of branches of root locus. So for the given transfer function, how many branches of root locus we will get, that is based on the number of poles or number of zeros. Suppose if number of poles are greater than number of zeros, number of poles are denoted with n and it is greater than m. Here n is number of poles and m is number of zeros. If poles are greater than zeros, then number of root locus branches is equal to n. Suppose if m greater than n, then number of root locus branches are equal to number of zeros. So here root locus branches is nothing but m. If n greater than m, then root locus branches are nothing but n. So which one is higher? So based on that, the number of, and root locus branches always starts from open loop poles and terminates on open loop 0. Suppose if zeros are not there in the given transfer function, then they will terminate at infinity. See here we have 2 poles. So root locus branches will start at pole number 1, that is at minus 2, and the branch of that root locus will ends at 0, that is at -1. Next we have second pole. Root locus branch will start at -3, but we have no other 0, only we have one 0. Then root locus branch will terminate at infinity. If poles are 2 means 0 should also be 2, then only the root locus branch will terminate at the zeros. But here number of poles are greater, therefore the root locus branches will terminate at infinity. Next, coming to the step number 2, determination of root locus on the real axis. So take the previous example, -1 we have 0, and at -2 we have a pole, and at -3 also we have a pole. Now the branch of root locus, whether it is lying on the real axis or not, we are going to check in this step. So for that, the condition is, how to check it is, take a test point. Suppose if I want to check whether the root locus exists between this pole and this 0, then I will take a test point here. So take a test point, let us assume it is P1. To the right of this test point, how many number of poles and zeros are existing? See here, only to the right of this test point only we have one 0. So 1 is an odd number. So if odd number of poles and zeros are exist to the right of the test point, then the root locus will exist between these two. So root locus branch will exist between this pole and 0. Next, I am going to check it between these two poles, whether the root locus is existing between these two or not. Now I am taking the test point P2. To the right of this test point, how many number of poles and zeros are there? This is -2 is one pole and -1 is one 0. So total 2 poles and zeros are there. So number of poles and zeros are 2. So 2 is a odd number, sorry, even number. Then root locus won't exist between this -3 and -2. Next, take another test point to check whether the root locus exists between this -3 and infinity. So take the test point as P3. To the right of this test point, how many number of poles and zeros are there? 1, 2 and 3. So total 3 number of poles and zeros are existing. 3 is an odd number. Therefore, root locus branch will exist between this pole and the infinity. So this is nothing but the root locus branch. So on the real axis, so the root locus exists at these two positions. This is the root locus branch. So this is also the root locus. So step number 2 is only determining the root locus on the real axis. For that, you have to consider a test point where you are testing whether the root locus is existing or not. At that, take a test point. Then to the right of the test point, if the number of poles and zeros are odd, then there exists a root locus. Otherwise, root locus won't exist between that. Next, third step, angles of asymptotes and centroid. See, in the question, if the open loop transfer function is having a gain k, as the k value is increasing, the root locus moves away from the poles and zeros. So for higher values of k, the root locus branches are approximated by the asymptotes. Asymptotes are nothing but these are straight lines that continually approaches a given curve but doesn't meet it at any finite distance. So if you have a root locus curve like this, then asymptotes will be in parallel with this. It's a straight line. Continually approaches the given curve but doesn't meet it at any infinite distance. So that is called the asymptotes. This curve is the root locus and this is the asymptote. So to find out the angles of asymptotes, the formula is plus or minus 180 degrees into 2q plus 1 by n minus m. And here q values you have to consider from 0, 1 up to n minus m. where n is what? Number of poles, and m is number of zeros. So, using this formula you can find out the angles of asymptotes. And the number of asymptotes always equal to number of root locus branches going to infinity. See in this example, in the step 1, here how many root locus branches are going to infinity? We have 2 poles, but to terminate the root locus branch we have only 1 0. So, this pole at minus 2, that will terminate at 1 0, but pole at minus 3 position, that does not have any other 0, so to terminate, therefore this pole will terminate at infinity. So, in this example the number of poles terminating at infinity are nothing but 1. So, number of asymptotes we require 1. So, like that you have to find out the number of asymptotes. So, number of asymptotes is always equal to number of poles which are terminating at infinity. So, number of root locus branches which are terminating at infinity. So, we will write here number of asymptotes is equal to number of root locus branches terminates at infinity. Next, these asymptotes, they will intersect the real axis, then that intersection point is known as a centroid. The intersection point of asymptotes with real axis is known as centroid. To find out the centroid, the formula is centroid is equal to sum of poles minus sum of zeros by n minus m. N is number of poles and m is number of zeros. Sum of poles means what are the poles in the above example? We have minus 1, minus 3 are the poles. Is it minus 1, minus 3? Okay. Minus 2, minus 3 are the poles. So, sum of poles means minus 2, minus 3 minus sum of zeros. What is the zero value we have? Minus 1 by number of poles. Number of poles are 2 minus number of zeros are 1. So, like this you can find out the centroid, sum of poles minus sum of zeros by n minus m. Next, fourth step, determination of breakaway and break-in points. See, first of all, where the breakaway point and break-in points exist, that we should have an idea. So, if there is a root locus on real axis between two poles, so let us see this. Suppose I have two poles like this, and root locus branch exists between these two poles, then there exists a breakaway point. So, breakaway point always exists between two poles, and between those two poles root locus must be there. If there is no root locus between the two poles, then there won't be any breakaway point. So, two poles and root locus must be between the two poles, then only breakaway point will exist. And where this break-in point exists is, breakaway point always exists between two zeros. If you have two zeros and there exists a root locus branch, in the step 2 we determine the root locus branch on the real axis, right? So, if there exists a root locus branch between these two poles, then there exists a break-in point between these two. So, breakaway point exists always between two poles and break-in point exists always between two zeros. Suppose if the root locus is existing between one pole and 0. Suppose I have a pole and 0 like this, and there exists a root locus branch between them. If root locus branch exists between them, then whether the breakaway point exists or break-in point exists, we don't know. So maybe it may be a breakaway point or may not be a breakaway point, or it may be a break-in point or may not be a break-in point. So we cannot find that. So it may or may not be a breakaway or break-in point between one pole and 0. But between two poles, breakaway point will exist. Between two zeros, break-in point will exist. And the procedure to find out these breakaway and break-in points is, you have to take the characteristic equation, and from the characteristic equation write the equation for k. Then differentiate this k with respect to s and equate it to 0. Then you will get some roots of this equation. Those roots you have to substitute in the equation k. Then if the k value is positive and real, so that roots are the actual breakaway or break-in points. Suppose if the k value is a negative value or it consists of some imaginary value, then the roots are not the actual breakaway and break-in points, so they won't exist. How to find out the breakaway and break-in points is, first consider the characteristic equation from the given transfer function, then write the equation for k from that equation. Next, differentiate that equation with respect to s and equate it to 0. After that, find out the roots of that equation. Then let's substitute these roots in the equation of k. Then if the k value is equal to positive and real, then breakaway or break-in point will exist. Otherwise, no breakaway and break-in point will exist. So while doing the problem, you can understand clearly this. Next step, angle of departure and angle of arrival. Determining the angle of departure and angle of arrival. See, when the angle of departure will exist is, if there is a complex pole, then only this angle of departure will exist. And when there is a complex 0, then angle of arrival will exist. If there are no complex poles and zeros, there is no need to find out the angle of departure and arrival, because they won't exist. Whenever only the complex poles or complex zeros are exist in the given transfer function, then only this angle of departure or angle of arrival will exist. To find out the angle of departure at complex pole A, the formula is 180 minus sum of angles of vectors to the complex pole A from other poles plus sum of angles of vectors from complex pole to other zeros. So let's see how to find out this angle of departure. I am taking this as plane. Now let's mark the complex pole. So I have a complex pole that is at minus 2 plus j3. One complex pole, and it is complex poles are always in pairs, minus 2 plus or minus j3, right? So minus 2 plus j3, minus 2 minus j3. So these two are the complex pole. So if complex pole is there, means there exists a angle of departure. And mark some other poles. So let's assume there are other poles. This is one pole and there is a 0 here, and here also one 0, and at origin there is a pole. So these are, let's assume this, these are the poles and zeros in the given transfer function. Now I want to find out the angle of departure. So to find out the angle of departure, you have to draw the vectors from complex pole to the complex pole from other poles. So I am finding the angle of departure at this complex pole. Now draw the vector from other poles to this complex pole. This is one pole. From this pole I am drawing the vector to this. This is one vector drawn to the complex pole from this pole. Now what are the remaining poles? We have another pole here. So draw a vector from this pole to the complex pole. Next, from this pole also you have to draw one vector. Okay, from all the poles I have drawn the vectors to the complex pole. Now mark the angles. Let's assume the angle is, this is theta 1 and plus sum of angles of vectors from complex pole to other zeros. We have two zeros in this example. So draw the vectors from those zeros to this complex pole also. So draw a vector from the 0 to this complex pole A, and one more vector from this 0 to this complex pole. Now mark the angles. This is theta 1 and this is theta 2, and let's assume this is the angle theta 2. Next angle, this is theta 3, this is theta 4, and this is theta 5. So let's assume the distance from here to here. Let's assume this is A, the distance from here to here. Next, this total distance, let us assume this is, and this is one more distance from this to this, B, and this distance C, and this distance is D, and this is E. Just I am assuming the distances to find out these angles. Now sum of angles of vectors. So sum of angles means what are the angles from other poles to complex pole. So A is equal to angle of departure 180 minus theta 1 plus, next theta 2 is, it is at 0. So we should not consider this. Sum of angles of vector to the complex pole from other poles only. So this is one pole, next second pole is this. So this is theta 3. Next, where is the other pole? This is the next pole. So what is the angle here? Theta 5. So sum of these angles plus theta 5 plus sum of angles of vectors from complex pole to other zeros. Complex pole to other zero means this is the 0. What is the angle here? Theta 2. Next, another 0, this one. So here the angle is theta 4. So theta 2 plus theta 4. This is the total formula. But we don't know these angles, right? How to find out this theta 1? To find out this theta 1, so you can observe here this total is the 180 degrees. But I want only this angle theta 1. If you find this inside angle and subtract that angle from 180, then you will get theta 1. And this is a right angle triangle. If you observe, this is the 90 degree. This is the right angle triangle and I am finding this angle. Let us assume x. And what is this distance? This distance we assumed as A. And this from here to here, the distance we assumed as B. Now x angle x is equal to tan inverse A by B. But I want which angle? Theta 1 angle. So how to find out theta 1? From the total 180 degrees, if you subtract this x angle, then you will get theta 1. Therefore, theta 1 is equal to 180 degrees minus tan inverse A by B. This is the formula for theta 1. Next, theta 2. So theta, where is theta 2? This is theta 2. So theta 2 also like this. This total angle is 180. So for getting theta 2 also, you have to subtract the angle from 180. 180 minus tan inverse. So this distance is A, and this distance here it is only C. So A by C. Next, theta 3 angle is 90 degrees directly. This is the angle theta 3. Next, theta 4. So theta 4, it is tan inverse. Directly from the right angle triangle, you will get this right angle triangle. Theta 4 is equal to tan inverse of this is A, and this distance is D, A by D. Next, theta 5 angle is equal to tan inverse. This is theta 5. You can consider this right angle triangle. Tan inverse A by, from here to here, what is the distance? E. So A by E. This is theta 5 angle. So this is the angle of departure at the complex pole A, and another complex pole, this is A conjugate. So the angle of departure at another complex pole will be the complementary angle only. Suppose if here you got a positive angle, at A dash, what will you get? Opposite. If at A, if you get negative angle, then at A complement means the angle will be positive. So you have to consider the opposite sign of the angle. Same way you can do it for the finding angle of arrival at complex 0. And next step, point of intersection of root locus with imaginary axis. So where the root locus is intersecting the imaginary axis, for that first consider the characteristic equation, then replace S with j omega in the characteristic equation. So after replacing this, separate the real parts and imaginary parts and equate it to 0. Real part is equal to 0 and imaginary part is equal to 0. Then you will get the values of omega and k. So whatever the values of omega you are getting, that is nothing but the crossing point on the imaginary axis. So that's it. So these are the steps to draw the root locus.